right. Now what you've truly been waiting for, another Dr. Kelly original reaction production. The explanation of oxidation reduction, or redox. Perhaps one of the most important concepts in all of chemistry. If you're going into the power industry, if you're going into the health industry, or Lord help you if you want to be a biologist for some silly reason, oxidation reduction is perhaps the reason you took this class. So without further ado, let's get things started with a bang. Alright, I always like to begin our discussion of oxidation reduction with a quick reaction. And this is perhaps one of my favorites. I've been doing it since I was a little kid. It's the reaction of aluminum and iron. And believe it or not, you've been doing it since you were a little kid too. Have you ever looked at a cap gun? You cut open those little bags, or your cap that comes with your cap gun, and you see this powder there, and you're all excited, and you're saying, oh wow, I've got gunpowder in here. No, that little powder there is actually rust, or iron 3 oxide. And if you look at the hammer of your cap gun, you'll notice it's aluminum. This reaction between aluminum and iron 3 oxide is a classic example of a oxidation reduction reaction. So let's observe it together here. All right, there's no doubt about it that you are definitely seeing a you are definitely seeing a chemical reaction there, right? There's a lovely picture to end that one on. And there's no doubt about it that you were definitely seeing a chemical reaction. You could even see energy was being exchanged there. This example of an oxidation reduction reaction is where we're going to begin our discussion of redox. Alright, the reaction you saw in the demonstration was the reaction of solid aluminum with rust to yield aluminum oxide and iron. What really happened in that reaction? After all, you were visually able to see and hear that there was some energy being exchanged during that reaction. What happened during that reaction? To understand what happened during the reaction, it helps if we take a little inventory of each atom's electrons and protons. Over here, I have aluminum with no charge showing. So I have regular old aluminum with a total of 13 protons and 13 electrons. 13 protons, 13 electrons. Then I have iron, and my iron atoms over here have a total of 26 protons because they're iron. But if we were to name this compound, we'd name it iron 3 oxide. So iron in this compound actually has a +3 charge. So if it has a +3 charge, that means it only has 23 electrons instead of the normal 26 of neutral iron. Then we have oxygen, and our oxygen's in an ionic compound, so that means it has 8 protons and 10 electrons. Because again, oxygen's in an ionic compound, so it has a -2 charge. When we move across to the other side of our arrow here, our aluminum is now in an ionic compound. And aluminum in an ionic compound, you remember, is always aluminum +3. So our aluminum right here has 13 protons and only 10 electrons. Our oxygen's in an ionic compound, and it hasn't changed. In an ionic compound, it's still going to be oxygen 2- with 8 protons and 8 electrons. Iron, however, is now by itself, and there's no charge showing over here, is there? That means that our iron now has 26 protons and 26 electrons. So if we look at what happened on a atomic level, or on the level of on the level of the atoms, what we can see is that we had aluminum going from aluminum solid to aluminum plus 3. In other words, we had aluminum going from aluminum with 13 protons and 13 electrons to aluminum with 13 protons and 10 electrons. So we had a situation where our aluminum lost 3 of its electrons. Conversely, we had iron in this equation, starting off as iron 3 with 26 protons and 23 electrons to form iron neutral with 26 protons and 26 electrons. So that means during the course of this reaction, our iron actually picked up 3 electrons from some place. This exchange of electrons between the aluminum and the iron, which is what happened in this reaction, this exchange of electrons between our aluminum and our iron is referred to as oxidation reduction, or redox. Specifically, we would say that our iron gained electron, and therefore our iron 3 gained electrons, and therefore our iron 3 was being reduced. Our aluminum lost electrons, and therefore we would say that our aluminum is being oxidized. The process of gaining electrons in a chemical reaction is referred to as reduction. Why? Because the charge of the atom winds up being reduced, right? We had iron here at 3 plus, and when it gained the electrons, it went to a charge of 0. Aluminum, which lost electrons, is referred to as being oxidized. Because we call the process of losing electrons as being oxidized. Why? Well, if you look in this reaction, our aluminum, which is oxidized, gained oxygen atoms during the course of the reaction, correct? And that's a common pattern. Elements that wind up having to give up electrons in a chemical reaction are often being combined with oxygens. Therefore, we refer to the process of losing electrons as being oxidized. Now, we can't create or destroy matter. So if somebody is gaining electrons, can it gain electrons if no one's losing them? Can somebody lose electrons if no one's gaining them? Of course not. That's why we refer to oxidation reduction as simply redox, right? They're like love and marriage. You can't have one without the other. Yes? All right, so let's formalize our definitions real quickly here, and I realize there's some problems with this reaction. We'll get back to it here in a second. Reduction is the gain of electrons. Oxidation is the loss of electrons. You can remember it from the acronym oil rig, or rig oil. Oxidation is lost, reduction is gain. Reduction is loss, oxidation is gain. And that's how I remember it. For those of the biologists in the crowd, you can also go, Leo says grrr, because I think that goes well with King Philip cries, oh for goodness sakes, because you know, King Leo's obviously a lion who would also say grr. So Leo says grr, loss electron is oxidation, gain of electron is reduction. Now would be a really good time for you to write down McDonald's. Everybody write down McDonald's. Old McDonald's had a restaurant. E-I-E-I-O. Actually, the guy's name was Croc, but that's beside the point. Everybody write down McDonald's. Okay, So if oxidation and reduction are paired processes, meaning if something is being reduced, it's causing something else to be oxidized, then we can use two terms that I think are the most confusing, disastrous terms in all of chemistry. And that's the term of oxidizing agent and reducing agent. If you're a rich and powerful person, I shouldn't say that. If you're a rich and powerful celebrity, you have somebody whose job it is to make things happen for you, and that person's called your agent. So, a reducing agent is something that causes something else to be reduced. In the context of our reaction here, aluminum is being oxidized. That means it's causing something else to be reduced. So since aluminum's being oxidized, that means it's the reducing agent. Conversely, my iron here is being reduced. It's gaining electrons. That means it's causing somebody else to lose them. So since it's causing somebody else to be oxidized, it's known as the oxidizing agent. I think these two terms are the worst terms in all of chemistry. The way I keep them straight is I also think of the word agent meaning opposite. Whatever is happening to a substance, it's the opposite agent. Whatever happens to a substance, it's the opposite agent. Let's cut through the clutter here. Let's look at another example. In this example, we're going to react copper solid with aqueous silver. And the result will be our silver coming out of solution as a solid and copper entering solution. I would point out, well, let's go ahead and balance it. May change my mind again in a second, but let's balance it for now. And that's the reaction we're going to view here. All right. What we have here is we have some silver ions in solution. To that solution of silver ion, I have a piece of pure copper. I've sanded it was tarnished a little, so those little streaks you see there are a little bit of tarnish that I've tried to sand off with some sandpaper. But you see I have pure copper here. When I place the pure copper in my silver nitrate, we're going to see an oxidation reduction reaction occur. The copper will lose electrons, the silver will gain electrons, and we'll be able to see the silver actually come out of solution on the surface of the copper. I'm hoping that my silver solution isn't depleted here. Exceedingly dark and woolly there. Actually come out of solution on the surface of the copper. I'm hoping that my silver solution isn't depleted here. It's getting darker and darker and darker. Probably going to make people seasick here. Change the angle. I'm the only person who can shoot a video and make people seasick filming a stationary object. But what you'll notice is it's getting very dark, right? My nice shiny copper is now dark. It's not a bad camera work. It is actually getting dark here. And as we go forward, it's going to get exceedingly dark and woolly there. I often do this during Christmas, where I cut my copper in the shape of a Christmas tree, and it'll grow pine needles here for us in a second. But as you can see, it's turning black from the silver coming out on the surface of my copper. and it's looking a little fuzzy around the edges now, you can see. That's not bad camera work. It's the fact, or cheap iPad camera, it's the fact that it is indeed getting fuzzy there. So you can see the silver coming out on the surface of the solution there very easily. Alright, so you can see that when we place the copper in the silver ion solution, we did indeed get silver to form on the surface of our copper. Classic demo. Let's take a look at a very simple reaction. The reaction of solid copper with aqueous silver ion to yield the copper 2 ion and solid silver. In this reaction, it's much clearer to see what's happening. First of all, let's state our goals. Our goal is going to be to determine who is the oxidizing agent, and the oxidizing agent will be remember, it's the opposite. So the oxidizing agent will be the species that is being reduced. And we also want to know who is the reducing agent. And that will be the species. I always think of Planet of the Apes whenever I write the word species. Get your paws off of me. All right. The species that is this Holden-Caulfield trip was brought to you by the letter R for reducing agent. The species that is being oxidized. If we look at this reaction, it's really obvious who's losing electrons and who's gaining them. If we take a look at our copper is going from having no charge to having a positive charge. If something's developing a positive charge, that means it must have lost some of its electrons. So copper is going from copper solid to copper 2 aqueous. That means it's being oxidized. If we were to take an inventory of it, for example, we would see that copper is going from a situation where it had 29 protons and 29 electrons to a situation where it has 29 protons and 27 electrons. Speaking of which, at the moment, the way I've written this chemical equation, I've destroyed matter, right? Because over here, I have 29 electrons, but over here I only have 27. So because my copper's lost 2 electrons, and I don't want to destroy matter here, I'm going to write those 2 electrons out there. What I've written here, where I've balanced out my electrons and I've shown the process of copper being oxidized here, this is referred to as a oxidation it's referred to as an oxidation half reaction. So this would be known as a half reaction because I've shown the oxidation part of the reaction. You now also understand why in the last slide I wrote those 2 electrons out there, because I have 29 electrons over here, 27 electrons over here, so I need to have 2 electrons over here to balance out, or else I've destroyed those electrons. The copper atom over here is losing electrons, so that means it's being oxidized, and that also makes it the reducing agent. It loses the electrons, so it's the reducing agent. It's being oxidized because it loses electrons. Oil rig. Oxidation is loss of electrons, and our copper atom clearly lost electrons. Our silver atom, on the other hand, starts off as the silver ion and goes to become solid silver with no charge. Again, if we were to take inventory here, we have a situation where we have 47 protons on this side, 46 electrons on this side, because we have a +1 charge. Over here we have 47 protons and 47 electrons because we have a neutral charge. Surprise, surprise, I've created energy, right? I've created matter. Because after all, I have 47 electrons on this side and only have 46 over here. I can't create or destroy matter. So to balance this half reaction, I have to have this extra electron right there. So as we look at this, we see that during the course of the chemical reaction, my silver ion is gaining an electron, going from 46 to 47 electrons. That means it's being reduced. My silver ion is being reduced, and it's causing something else to lose electrons, so that means my silver ion is the oxidizing agent. So my silver ion is the oxidizing agent. And this would be the reduction half reaction. Looking at the half reactions in oxidation and reduction is going to be very important. Matter of fact, a significant portion of this lecture will be spent on how to write and develop and balance those half reactions. But for now, just looking at these two half reactions helps us explain a question some of you may have had when we looked at the overall reaction up here. If you look at this overall reaction, some of you may have been questioning, why do we have a 2 in front of my silver here? After all, if I didn't have that 2, wouldn't my reaction still be balanced if I didn't have that 2 in front of my silvers? No, it wouldn't. It wouldn't be balanced at all. And here's why. If I don't have the 2 here and here, my electrons aren't balanced. What do I mean my electrons aren't balanced? If we look at our half reactions, for every 1 atom of copper that I oxidize, I go from copper 0 to copper plus 2, and I give up 2 electrons. So going from this element to this, going from this copper to this copper, I give up 2 electrons. I have to have something to take those 2 electrons. Each silver only takes 1 electron. So if I'm to dispose of 2 electrons, I need this reaction right here, this half reaction, to occur twice. If I don't have that reaction occurring twice, then I have a homeless electron. So to balance out my chemical equation and make sure my number of electrons are balanced in this overall chemical reaction, I have to have that 2 there in front of my silver. Otherwise, my electrons don't cancel out. By placing that 2 in front of my silver, I allow my electrons to cancel out. For example, a concept that's going to become really important to us as we move forward in chemistry is the fact that you can add chemical equations together just like you can mathematical equations. When we balance redox reactions, we always add these half reactions in such a fashion that electrons cancel out. If I want my electrons to cancel out, then I need to multiply my top equation through by 2. When I do that, that gives me 2 electrons on this side to cancel out the 2 electrons on that side. So that when I add my 2 equations together, my electrons wind up disappearing. Okay, so hopefully you have a good understanding of oxidizing reducing agent, how to and what oxidation means and what reduction means. What we want to do now is we want to learn a series of rules that will allow us to look at a complex equation and determine who's being reduced, who's being oxidized, who's the reducing agent, who's the oxidation agent. There are some easy clues for identifying oxidation reduction reagents, and before we do this, I got to balance this here. Otherwise, it's going to drive me bonkers. I'd planned to use this demonstration to talk about those electron imbalances, but I went freestyle, and again, I can't help it. I'm like a jazz poet when it comes to chemistry. But at any rate, identifying redox reactions and identifying who's being oxidized, which makes them the reducing agent, and the oxidizing agent, who is, of course, being reduced. If something is being oxidized, it's going to lose electrons. Its oxidation number is going to become more positive. What do I mean by oxidation number? Oxidation number is a fancy way of saying charge. We'll go into it in more detail here in a second, but for the moment, think charge. Its charge is going to become more positive. If something gains oxygen during a reaction, then that sometimes means it's being oxidized. If something loses hydrogen during a reaction, that means it's being oxidized, which would also mean it's the reducing agent. The clues for an oxidizing agent, or something that's being reduced, are the exact opposite. An oxidizing agent will gain electrons. The oxidation number, again, think charge. We'll get to the full definition of oxidation number in a second. Becomes more negative. And something that is being reduced often loses oxygen during a reaction, and it often gains hydrogen during a reaction. This loss and gain of hydrogen is really big with you biologists. Think about it. When you learn that your Krebs cycles and all that, where you're passing those NADHs along, what are those NADs really passing between each other? They're passing hydrogens, right? You're transporting your electron along with a hydrogen. In all those metabolic pathways you've learned in biology, you're passing an electron, and whenever you pass an electron, you're passing a hydrogen with it. So it makes sense that something being reduced will sometimes see a gain of hydrogen. All right, let's take a look at these clues in the context of our favorite reaction. If we look at our favorite reaction here, we can see that during the course of our reaction, aluminum is gaining oxygen. So that means that, or it's a clue that, aluminum is being oxidized in this reaction. And if it's being oxidized, that means it's the reducing agent. Iron, on the other hand, in this reaction, my iron, on the other hand, is losing oxygen. And that's one of our clues that a substance is being reduced. Since our iron loses the oxygen and it's being reduced, that means it's the oxidizing agent. Chemistry's easy, life is hard, yes? Let's take a look at another. If we take a look at another example, let's make it hot in here. we have the combustion of natural gas. Wait a second, combustion reactions are oxidation reduction reactions? Let's find out, shall we? If we look at our carbon over here, as our carbon moves across the reaction, it's gaining oxygen atoms, yes, and it's losing hydrogen atoms. Both of which are signs that something is being oxidized. And if something's being oxidized, it's causing the opposite to happen, so it must be the reducing agent. Our oxygen, if we look at it, during the course of this reaction, our oxygen it's gaining hydrogen. And we said that when something gains hydrogen, that's a clue that it's being reduced. And if something's being reduced, it's causing the opposite to happen, which makes it the, guess what? The oxidizing agent. I wonder if that's why they use the term. Wouldn't that be something else if they came up with the term oxidizing agent, because oxygen's an oxidizing agent? Amazing. And that is, in fact, what's happening during this chemical reaction. But wait a second, Dr. Kelly. Everything you're showing me here is a covalent compound. So how is anything gaining or losing electrons? After all, in covalent compounds, they share, right? Yeah, they do. Covalent compounds a big happy marriage until it comes time for the divorce. And then they have to have a way of dividing up the property. And that's where oxidation numbers come in. With oxidation numbers, you treat atoms in a covalent compound like the covalent compound is a ionic compound. I'm sorry, I got distracted pushing buttons. We've got gas here. 2 oxygens. High-tech graphics. Did I have a 2 in the last version of this equation? That'd be embarrassing if I had that last equation incorrectly balanced, and if I did, please forgive me. Forgive me, periodic table. All right, but here's our reaction again. Let's look at it in the current context of oxidation numbers. Oxidation numbers are a way of assigning ownership of the electrons in a compound. There are some very easy rules for determining the oxidation numbers of the elements in a compound. And we'll go over those well, why in a second? Why not right now? All right, here are the rules for assigning oxidation numbers. If you look in this handout, I've got one slide that condenses all these rules into 1 or 2 slides. And I would print that out and have that in front of you while you're doing the homework. And I hope you've printed it out right now anyway. But at any rate, I digress. The oxidation number, or oxidation state, is a value that indicates whether an atom is neutral, electron-rich, or electron-poor in the context of a particular molecule. The rules for assigning oxidation number, we're going to detail them through here in a second. But I would tell you that if you ever forget them or panic or find yourself panicking on an exam, if you simply treat every compound out there like it's ionic and follow those ionic rules for determining the charge on something in an ionic compound, you'll discover that they pretty well have you covered. So let's take a look here. First rule. An atom in its elemental state has an oxidation number of 0. In other words, if an atom is by itself, or an element is by itself with no charge showing, it has an oxidation number of 0. In other words, it's done nothing chemically to gain or lose electrons. So its oxidation number is 0. An atom in a monatomic ion has an oxidation number identical to its charge. In other words, if you look at an ion, such as aluminum, with a +3 showing, guess what its oxidation number is? +3. If you see oxygen by itself with a 2 negative, guess what its oxidation number is? 2 negative. Calcium, if you see an oxidation number of calcium by itself with a +2 charge, guess what? Its oxidation number is +2. Ah, now we're getting somewhere. First and foremost, an atom in a molecular compound or polyatomic ion usually has the same oxidation number it would have if it were a monatomic ion. What does it mean by that? It means that group 1A elements will usually be +1, group 2A elements will usually be +2, 6A elements 2 negative, group 7A elements -1. Some other guidelines to help us is hydrogen can be either +1 or -1. I hate this rule, by the way. Hydrogen will only be -1 if it's listed after a metal in a compound. Remember, when we're looking at ionic compounds, there's always a convention. In ionic compounds, we always write the positive ion first and the negative ion second. There are some freak compounds called hydrides out there, and I mean they're freak, okay? I think they exist just for the sole purpose of messing people up on oxidation reduction tests, okay? Okay? Suddenly I'm obsessed with 0 temperature. But in these contexts where you see hydrogen after a metal, that's the only time it's going to be -1. You should program yourself to think that hydrogen's +1, but remember that if your chemistry professor is feeling evil, if that hydrogen's listed after a metal, it can have a charge of -1. All the other times your hydrogen's going to have a +1 charge. Oxygen usually has an oxidation number of 2 negative. The only time you see oxygen really without a 2 negative is when you're looking at something like peroxide. Peroxide's a polyatomic ion. But that's the rare circumstance where you'll find oxygen without a -2 charge, or oxygen by itself. Right, oxygen by itself, like that, then it has an oxidation number of 0. But 99.9% of the time, when you see oxygen, it will be 2 negative. And matter of fact, let's formalize it. If you look at the examples they gave you down here, water, oxygen's 2 negative. This compound they've stretched out for you is hydrogen peroxide. Oxygen's only really going to be -1 in peroxides. Alright, chemistry is easy, life is hard. Let's keep moving. Halogens, in other words, my group 7A elements, are usually -1. The exceptions halogens usually have an oxidation number of -1, except when they're bonded to a more electronegative element. Remember, electronegativity increases this way and increases this way. Since halogens are about as far as you can go over about as far as you can go over to the right, that means there's very few things that are more electronegative to them. As a matter of fact, basically the only things that you can bond to a halogen that will make it be something other than -1 would be oxygen. Oxygen's more electronegative. It's going to get to be too negative and force the halogens to be something else, like +1s. Or another halogen. Sometimes nitrogen as well there. If a halogen is bonded to a more electronegative halogen, for example, iodine and chlorine, chlorine's more electronegative because it's higher up. So chlorine gets to be the -1, which will force iodine to be a +1. That brings me to something else that we haven't mentioned. The sum of the oxidation numbers is 0 for a neutral compound and is equal to the net charge for a polyatomic ion. In other words, if you run into an element not covered by one of those rules we've just discovered, you can always figure out its oxidation number by doing that same math you used to determine the charge on a metal in an ionic compound. For example, let's take a look at sulfurous acid. I want to know the oxidation number of sulfur here. How can I figure it out? Well, I know a rule for hydrogen. I have 2 hydrogens, and according to my rules, hydrogen has a +1 charge. I don't know the oxidation number on my sulfur. I have 3 oxygens. Each one of those oxygens has a -2 charge, according to my oxidation rules. The sum of these has to be equal to 0. So +2 plus x plus a -6 has to be equal to 0. So x would have to be +4. So the oxidation number on my sulfur in this compound has to be 4 positive. Oxidation numbers for elements not covered by our rules are very much situational dependent. For example, sulfur is +4 in sulfurous acid. What about in sulfuric acid? If we look at sulfuric acid here, once again I have 2 hydrogens at +1 each. I have 1 sulfur, and then I have 4 oxygens at 2 negative each. In this scenario, x would be 6, right? So sulfur would have an oxidation number of 6 in this compound. So oxidation number is very, very much situational dependent. Another way to think about oxidation number is oxidation numbers are 100% pure fiction. They're something we drew up as an accounting tool to help us conceptualize what's going on. So they're very much situational dependent. Sulfur is not always going to have the same oxidation number here. We can do oxidation numbers with polyatomic ions if we want to. For example, if we wanted to take a look at chromate here, not chromate, dichromate. I have the dichromate polyatomic ion. I don't have a rule that involves chromium, but I have two of them. I have 7 oxygens, and each one of those oxygens has a 2 negative charge because it's oxygen, not because there's a negative 2 there. According to our rules, the sum of the oxidation number has to equal the charge on the molecule. So my oxidation numbers, instead of equaling 0 for dichromate, are going to equal negative 2. So 2x plus 7 times negative 2 has to equal negative 2. So 2x minus 14 equals 2 negative. So x has to be 6. So the oxidation number on chromium in this compound would be 6 positive. Let's take a look at some more examples. Here's the slide I was talking about. If you haven't already, print this out, and I printed out full page style so that I had it with me while I was working the homework. Alright, assign oxidation numbers to each atom in the following substances. Alright, let's start with the center for DC. Let's start with CDS here first, or cadmium sulf, or cadmium 2. Well, I can't say the name because that'll give away the oxidation numbers now, won't it? We take a look at this compound. It's an ionic compound. We like ionic compounds when it comes to oxidation numbers because it means they're simple. Sulfur's in group 6A, so we know it's going to be 2 negative. Cadmium, if it's bonded to sulfur, has to be 2 positive, plus it lives under the staircase steps like Harry Potter, so we knew it was 2 positive anyway. Chemistry is easy, life is hard. Now we come to aloha. We look at this compound, and the first thing that jumps to mind is our rule about hydrogen that says hydrogen's positive 1. And we're getting ready to call hydrogen positive 1, and then it hits us from out of the blue that hydrogen here is in the second position. It's in the second position next to a metal. And remember, our convention always says that we write the positive ions, then the negative ones. So that must mean that our hydrogen isn't positive 1 like it normally is, but a negative 1. And aluminum, we know, is 3 plus when it comes to compounds. Chemistry is easy, life is hard so far. Here's something that provides us with a little bit of a challenge. Thiosulfate. First of all, it's a polyatomic ion, so instead of being 0, the sum of our oxidation numbers has to be 2 negative. We have 3 oxygens, and each of them has a 2 negative charge by rule. Then we have 2 sulfurs. We don't know the charge in each one of those sulfurs, but we know the sum of the charges has to be 2 negative, so negative 6 plus 2x equals 2 negative. So 2x equals 4. Wow, chemistry is easy and life is hard. That means that sulfur would have to be plus 2 in this scenario. Let's look at our last scenario. Well, we did this last scenario, so let's not waste time with that one. We did chromate on the last one, dichromate on the last one. Let's keep moving. When methane is burned in oxygen, the product contains carbon dioxide. The oxidation numbers of carbon in methane and carbon dioxide respectively are, this brings us full circle. I love it when we come full circle. It's almost like I planned it. Oh, wait, I did! Because I'm brilliant. Nearly as brilliant as Wendy's menu. Wendy's can't make a bad burger. Why don't you write down Wendy's? Everybody write down Wendy's. We said that the combustion of methane was an oxidation reduction reaction. And it is. And we now have the tools to absolutely concretely prove it. If we look here, we have carbon bound with hydrogen. Well, by rule, we have 4 carbons, and each one of those, we have 4 hydrogens in methane, and each one of those hydrogens has a +1 charge. We don't know the charge on carbon, but we know the sum of the oxidation numbers has to be 0, since methane's a molecule without a charge. So, x plus 4 is 0, x would have to be -4. So in methane, carbon has an oxidation number of -4. Our oxygen over here is an element by itself, so it has an oxidation number of 0. When we go to the other side of this arrow here, and we look at carbon dioxide, we have 2 oxygens, each with a 2 negative charge. We don't know the charge on our carbon and carbon dioxide, but we know that the sum of our charges has to equal 0. So x plus -4 is 0, so x would be +4 in carbon dioxide. And then when we look at our water, according to our rules, hydrogen's +1, and oxygen in a compound is usually 2 negative. So if we look at this reaction, and I want to, oh, by the way, just so we don't get lost, it would be -4, +4, right? Since we're doing methane and carbon dioxide respectively, it'll be E. Answer E. E is the right answer. All right, go away. You're bugging me. All right. Now we look at this one here. If we look, we have carbon in our methane going from a -4 to carbon dioxide where it's +4. So its charge has become more positive. That means it's being oxidized. It's lost electrons. It went from a situation where it had possession of 4 extra electrons to a situation where it's not only lost its 4 extra electrons, but now it has to give up 4 electrons to the oxygen. So we would say that our carbon and methane is being oxidized. So who's being reduced? Aha! Our oxygen. Look at our oxygen. Our oxygen went from a situation where it had no extra electrons, an oxidation state of 0, to a situation in water and in carbon dioxide where it had possession of 2 extra electrons. In other words, its oxidation state became more negative, or it was reduced. So our oxygen was reduced, making it, of course, the oxidizing agent. Oxidizing agent. I'm just going to make a bunch of scribbles and pretend that you can't read my writing. And then being oxidized, and then this methane over here, since it's being oxidized, that makes it the reducing agent. A substance whose oxidation number becomes more positive is being oxidized, so it is the reducing agent. A substance whose oxidation number becomes more negative is being reduced, so it is the oxidizing agent. Write that down, tattoo it on your arm, put it in a locked box, do whatever it takes to get that in your memory. Let's keep rolling and apply these principles to an actual chemical equation. That's right, everything we've done so far in one gloriously awesome example. All right, identify the oxidizing and reducing agents in each of the following reactions. Well, this first one is like so easy it's almost insulting. First thing we want to do is assign oxidation numbers to everything. So calcium is an element by itself, so it has an oxidation number of 0. Our hydrogen ion, in this case, is an ion made of one element with its charge showing, so the charge is equal to the oxidation number. So our hydrogen here is +1. Then we have calcium over here, the calcium ion, forgive me, as a monatomic ion with its charge showing. So the charge is the same thing as the oxidation number. So over here, calcium's 2+. Then we have hydrogen gas. That's an element by itself. An element by itself with no charge showing has a charge of 0. So we have step 2, determine who's becoming more positive. More positive is being oxidized. You can remember that because the OPP is fine with me. Yes, that's right. I just tried to rap. Deal. So oxidation is more positive. So we've gone from calcium to calcium 2+. So we've gone from 0 to 2+, so our calcium is becoming more positive, meaning it's being oxidized. And if something's being oxidized, it's causing something else to be reduced. So our calcium is our reducing agent. Agent means opposite. So if calcium is being oxidized, that means it's the reducing agent. Our hydrogen is becoming more negative. Step 3, identify who's being more negative. So we're going from +1 to 0. So that means it's being reduced. And that means our hydrogen right there is our reducing agent. Chemistry's easy, life is hard. Let's work another one and keep the party going. Where did that thing go? Aha. All right. Again, this should be fast. The oxidation numbers are all definitely out in the open here. +2 for the iron, 0 for the chlorine since it's an element by itself. Iron ion over here is the iron 3 ion, so it's a +3. And the chloride ion over here is -1. So our iron 2 is becoming more positive. So it's being oxidized, which means it's the reducing agent. Our chlorine's going from 0 to -1, so it's becoming more negative, which means it's being reduced, which makes it the opposite agent. Oxidizing agent. Agent means opposite. Chemistry's easy, life is hard. Why don't you write down Jack in the Box? Everybody write down Jack in the Box. Who doesn't like a good Jack in the Box? Well, despite that whole botulism scare in the 90s. But, what's that all about? Jack in the Box. I hope everybody wrote down Jack in the Box. And just for the lawyers, people out there, I'm not sure it was botulism. It was in the 90s. I forget. It could have been E. coli or some other thing. But at any rate, I digress. Just write down Jack in the Box.